Hello, in this section we're covering another prerequisite. Hopefully this is a review for most of you, if not all of you. We're going to cover exponents and radicals. Specifically, we're talking about properties of exponents, using scientific notation, properties of radicals, simplifying radicals. We're going to talk about rationalizing denominators and numerators, and then using the properties of rational exponents.
Specifically, we're talking about properties of exponents.
So first of all, let's talk about what an exponent actually is. So exponents are used for multiplying. If I was wanting to multiply something over and over and over and over again, I could say, as this example shows, a times a times a times a times a. Well, what I've done is I've taken the letter a and multiplied it 5 times. So instead of saying a times a times a times a times a, I could write that as a to the 5th power. So 5 is your exponent, and it tells you we're going to multiply the base a 5 times. Similarly, if I wanted to multiply the number negative 4 3 times, instead of saying negative 4 times negative 4 times negative 4, I could say negative 4 cubed, or negative 4 to the 3rd power. We'll point out again later, but I want you to notice that I am multiplying negative 4. So if I'm multiplying negative 4 repeatedly, I do have parentheses around that negative 4, and that's to make sure the negative sign stays with the 4. It's very, very important. We could also do this with numbers and variables. 2x times 2x times 2x times 2x is simply 2x to the 4th power. So exponential notation. If a is any real number and n is any positive integer, then a to the n is the same thing as a times a times a times a times a. And we're going to do that n times. So the exponent tells you how many times you're going to do that. Again, n is the exponent, and a is the base. You read a to the n power as a to the nth power.
And we're going to do that.
An exponent can also be negative.
Tells you how many times you're going to do that.
So that's something to remember. We can have a negative exponent, but we're going to do some math with it. And what does a negative exponent really mean? We'll talk about that in just a little bit.
An exponent can also be negative.
So here are some properties. I know it might be hard to read. You do have this packet available to you to download. You can find it in your syllabus, and you can see it a little bit better there. Property 3 here shows a to the negative nth power. And I'm going to go ahead and write that out. It's a little hard to read here. So if I have a and a negative exponent, I can get rid of that negative exponent. Think about the fact that a to the negative n power over a 1, right? If I divide anything by 1, it doesn't change the value. So you can think of anything as being a fraction by putting it over a 1.
I can get rid of that negative exponent.
Well, what I can do to change that negative exponent into a positive exponent is I'm actually going to
divide anything by 1, it doesn't change the value. So
this piece right here, the whole thing to the bottom. But as soon as it passes that fraction bar,
the
negative n changes signs. So the base will stay the same, but by passing through that fraction bar, it changes the sign of your exponent. So a to the negative n is equal to 1 over a to the nth power. So I now have the base the same at a, the exponent changed signs, but instead of being in the numerator, it's now in the denominator. And we can also do that the other way. If we had the negative in the bottom, I'm just going to go write it on the other side. If I had 1 over a to the negative n, now my base of a with an exponent of negative n is in the denominator. If I pass it to the top, it's also passing through that fraction bar. So because it's passing through that fraction bar, that's going to come up to the top here, that negative n becomes a positive n.
Now my base of a with an exponent of negative n.
So a very important property of negative exponents. And also know that 1 over a to the n can also be written as 1 over a, that whole thing raised to the nth power.
So a very important property of negative exponents. And
all right, so there's some other properties there that you can look through. If you have any questions, feel free to message me. We'll be happy to talk about it there.
That whole thing raised to the
It's important to recognize the difference between the expressions such as negative 4 in parentheses to the 4th power and negative 2
right, so
to
there's
the
some other
fourth power.
properties there.
When you put parentheses around the negative 2, that means that I'm taking that negative 2 and multiplying it repeatedly 4 times.
Such as negative 4 in parentheses
But
to the fourth power.
if I don't put parentheses around it, I can read that as the opposite of 2 to the fourth power. In this case, the exponent of 4 is only on the 2. So negative 2 to the fourth power would be the same thing as negative, and if I put parentheses around the 2 to the fourth power to just intensify the fact that the negative sign is not with that 2, and the exponent is only on the 2. So if I put parentheses around it, negative 2 to the fourth power, negative 2 times negative 2 is positive 4, times another negative 2 would be negative 8, times another negative 2 would be a positive 16. So when you put parentheses around it, you get a positive 16. Without the parentheses, again, the exponent is only on the 2, so that's only 2 to the fourth power. 2 times 2 is 4, times 2 is 8, times 2 is 16, but there's a negative in front of it. So negative 2 to the fourth power is negative 16. So be very, very careful when you're doing your math and know where parentheses should be and shouldn't be.
2 times 2 is 4, times 2 is 8, times 2 is 16. But there's
so let's look at some properties of exponents.
So negative 2 to the fourth power.
Two screens ago actually showed all the properties. I'm going to talk through them here. So on number 1, if I'm multiplying negative 3 times a times b to the fourth power, I'm multiplying that by 4 times a times b to the negative third power. What we do there is we look at it piece by piece. So negative 3 and 4, well, that's just two numbers. We can multiply those together. Negative 3 times 4 would be
multiplying that by
negative
4 times a
12.
times b to the negative third power. What we do
the next thing I have is a times a. You don't see an exponent there.
And 4.
The exponent is a 1. So I have a to the first times a to the first. When you have the same base, a and a, you multiply those together, you keep the base,
the next thing I have is an a times
and you add the exponents. So the exponents are 1 plus 1. I'm going to go ahead and write that out for this time.
So I have a to the
and
first
as I go on, I'm going to
kind
of stop writing these out.
The same base, a and a.
The next piece I have is b to the fourth power times b to the negative third power. So again, the bases are the same at b, so I'll keep the b.
And as I go on, I'm going to
and the exponents are, again, because I'm multiplying, the bases are going to be, the exponents will be added together. So my exponents are 4 plus
so again, the bases are the same
3.
at b, so I'll keep the b.
All right, so cleaning that up.
And the exponents are, again,
12.
because I'm multiplying, the bases
a to the 1 plus 1 would be a to the second power, or a
so
squared.
my exponents are 4 plus.
b to the 4 plus negative 3. Well, 4 plus negative 3 would be 1.
All right, so cleaning that up.
And so that would be
we have a
b to the
12.
first power. But again, exponents of 1 we don't write, so there's your
a to
answer.
the second power, or a squared. b to the 4 plus negative 3.
Part B.
4 plus negative 3.
I have a set of parentheses.
And so that would be
inside that set of parentheses, the whole thing is being raised to a third power. So
so
every single piece of this product inside the parentheses is being raised to the third power.
Part B.
So what that means is
I
that
have
2
a set of parentheses.
is raised to the third
Inside
power.
that set of parentheses, the whole
The
thing
x
is being raised to the third power. So every
And
single piece
the
of
y
this
squared
product inside
is
the
raised to the
parentheses
third
is being
power.
raised to the
Now I
third
put the
power.
y squared in parentheses
So what
so
that
that you
means
know that
is
is
that
one
2
single thing that I'm
is
raising
raised
to the third
third
power. And we'll do something with those
The
exponents in
x
just a
is
second.
raised to the third power.
Cleaning this up, 2 to the
And
third power would be
the
2
y
times 2 times 2.
squared is
Well, 2
raised
to the third power is
Now, I put
8.
the y squared in parentheses so that you
I
know
cannot
that
do
is one
anything with
single
x
thing
cubed,
that
so I
I'm
just
raising
keep
to the
it.
third power, and we'll do something with those
And
exponents
y
in just a
squared
second.
cubed. Okay,
Cleaning this up.
so
2
in
to the
example
third power would be
A,
2 times 2
I
times
was
2.
multiplying,
Well, 2 to the
the
third power
bases were the
is
same,
8.
so I added the exponents.
I
So
cannot
when
do anything with
multiplying,
x
you
cubed,
add
so
the
I just keep
exponents.
it.
On part B, I'm
And
taking y
y
squared
cubed.
and I'm
Okay.
cubing it. So I'm taking
in
a power
example
to a
A,
power.
I was
When you take a power to a
multiplying,
power,
the bases were the same,
that's a little
so
bit
I
more powerful
added
than
the
adding.
exponents.
So when you
So
take
in
a power to a
multiplying,
power,
you
you
add the
multiply
exponents.
those exponents.
On
So this
part
is going to
B,
end up
I'm
giving me
taking
y
y
to the
squared
2
and I'm
times
cubing
3,
it.
which is
So I'm
6,
taking a
so
power to
y
a power.
to the 6.
When you take a power to a power, that's a little bit more powerful than adding. So when you take a power
Part
to a
C.
power, you multiply
We look at
those
it.
exponents. So
Know
this is
your
gonna end up
order of
giving me y to
operations.
the 2
Remember
times
that
3,
you do
which is
anything in
6.
parentheses
So
first.
y
Well, in this
to the
case,
6.
I do have parentheses, but there's no math that I can do inside there. Next thing you want to look at are exponents.
Part C.
And I do have an
You
exponent.
look at it.
Right
know
here,
your order of operations.
Remember
have that you do anything in
an
parentheses
exponent.
first.
I have
well,
negative
case,
4a squared, which is
but
something
no
being raised to the 0 power.
Next thing you want to look
Well,
at
one of the
are
properties we
exponents.
had earlier stated that anything raised to the 0 power is 1. However, you cannot raise 0 to the 0 power.
Which is something
it's undefined.
being raised to the 0
so
power.
For this instance,
one of the
I'm
properties
going
we
to keep
had
my
earlier
3a.
stated that
I can't do
anything
anything with
raised
it.
to the 0 power is 1.
And I've got
However,
this whole thing, this whole
you
negative
cannot
4a squared
raise
that's raised to the 0
to
power.
the 0
Well,
power.
that's simply going to be 1.
It's undefined.
So all I have now
for
is
this
3a
instance,
times 1, which is
I'm gonna
3a.
keep my 3a.
Okay, now I do have a
I can't do
situation though.
anything with it.
Because
Now,
I
I've
am
got this
raising
whole
negative
thing, this
4a
whole negative
squared to
4a
the 0
squared is
power,
raised to the 0 power.
I must
that's
make
simply gonna
sure
be
that
1.
I account for the fact that
So
the
all I have
value
now
of
is
4a
3a times 1,
squared
which is 3a.
cannot
Okay, now
be
I do have a
0,
situation
again, because I cannot raise 0 to the 0
Because
power.
I'm raising negative 4a
I must
squared
make
to
the
the 0
statement that
power,
a
I must make sure that I account for the fact
be
that
0,
the value
because
of 4a
0 squared is 0.
cannot be 0.
0
again,
times
because I
negative
cannot
4
raise 0 to the
would be
0
0,
power.
and 0
So,
to the 0 power.
I must
is
make the
undefined.
statement that
So the correct answer for C would be 3a,
cannot
as long as
be
a is
0,
not equal to 0.
because 0 squared is 0.
Okay, part D.
0 times negative 4
kind of bring it down a little bit when I write that one out.
And 0 to the 0 power
So
is undefined.
I have a product
So
on the
correct
top. I
answer
have
for C
5
would
times
be
x cubed,
3a,
and I have
as
a y
long
in the
as a is
denominator.
not equal to 0.
That whole fraction is being raised
part
to the
D.
second power. I have
bring it down a
one
little
simple
bit when I write that
term inside
So
parentheses.
I have a product on the top.
Everything
I have 5
inside the
times x
parentheses
cubed,
is going
and
to
I
be
have
squared.
a y in the denominator.
So I have
that whole fraction
5
is
squared.
being raised to the second power.
I have x
I
cubed
have one simple
squared
term inside
divided by
parentheses.
y squared.
Everything inside the parentheses is going to
5
be
squared. That's
so
25.
I have 5 squared.
X cubed squared. Again, I'm raising a power to a power. So when you raise a power to a power, you multiply those exponents. So that gives me x to the 6th power.
5 squared
divided by
that's 25.
y squared. And I look at that and I see
again,
that I can't simplify anything, so we're done, and that is, in fact, the answer.
Exponents. So that gives me x to the 6th power.
The next slide is going to have these worked out. And you'll
yeah,
see that if you get the same answers that I got, number 1, letter A was negative 12a squared b. Letter B was 8x cubed y to the 6th. Letter C was 3a as long as a is not equal to 0.
And you'll see that you got the same answer.
And letter D is 25x to the 6th over y squared.
Letter B was 8x cubed.
So talk about some radicals and properties. A square root is a number is one of 2 equal factors. For example, 5 is a square root of 25 because 5 times 5 is 25. A cube root of a number is one of 3 equal factors, such as 125 is the same thing as 5 cubed, because 5 times 5 times 5 is 125. So we can say that the cubed root of 125 is 5. So here's our definition of an nth root of a number. If a and b are 2 real numbers, such that n is greater than or equal to 2,
times 5 is 125. So we can
and
say
positive.
The cube root
if a equals b to the nth power, then b is the nth root of a. If n was 2, the root is a square root. When n is 3, we say cube root.
And positive. If a equals b to
Some numbers have more than one nth root. For example, both 5 and negative 5 are square roots of 25.
The root is a square root.
The principal square root of 25 is the 5. So if I was to write the square root of 25,
some numbers have
I am asking for the principal square root of 25. So the square root of 25 is the positive root 5.
So if I was to write
the principal nth root of a number is defined as follows. The principal nth root, if a is a real number that has at least one nth root, the principal nth root of a is the nth root that has the same sign as a, is denoted by a radical symbol.
The principal nth root
this right here is read the principal nth root.
If a is a real number, it has at least one nth root. The principal nth root of
the
a
positive
is the
integer n greater than or equal to 2 is called the index.
It is denoted by a radical symbol.
So that right
so
there
this right here
is
is
the
read
index.
The principal nth root. So this is the nth root of a.
And the number a is the radicand. So whatever is inside the radical is called the radicand.
Is called the index. So that right there is the index.
If you do not see a number there, if you don't write the 2 down,
and the number a is the radicand. So whatever
right
is
here,
inside the radical is called
we
the
assume
radicand.
the index is 2. That's why we call it a square root. The plural of index is indices.
If you do not see a number there, if you don't write the 2 down, such as this right here.
Okay, a common misunderstanding about a square root sign. Some people say that a square root sign implies both a negative and positive. This is not true. If I see the square root, I'm simply asking for
a common misunderstanding
the principal
about square root
root.
Signs. Some people say that a square root sign
the square root of 4 is not plus or minus 2.
This is not true.
The square root of 4 is 2.
I'm simply asking for
negative square root of 4 is negative 2. If
so,
I wanted
the square root of
square
4
roots,
is not
I would say
plus or minus 2.
Or minus the square root of 4.
The square root of
that
4
is, in fact,
is 2.
plus or minus 2. So pay attention to what's being asked of you. If we're simply doing the math and finding the square root of something,
I would say
we want the principal square root.
Square root of 4. That is, in fact, plus or minus 2. So pay attention to what's being asked.
Some generalizations about the nth root of real numbers.
Doing the math,
if a is greater than 0,
we want the principal
and
square root.
N is even, meaning we have the nth root of a or negative nth root of a. For example, the fourth root of 81 is 3, because 3 to the fourth power is 81.
A is greater than 0.
Negative fourth root of 81 is negative 3, because negative 3 times negative 3 times negative 3 times negative 3 is also 81. So notice again, the first one, there is no negative sign in front, so I want to deposit 3 is my answer. The second one, I've put a negative up front, so the answer is negative 3.
Because negative 3 times negative 3 times
if a is between 0,
so notice again,
I'm sorry, if a is greater than 0 or less than 0.
Positive 3 is my answer.
So notice the difference between the first one. The first one, we were taking an even root. The second one, I'm taking an odd root. When taking an even root, a must be positive.
A is greater than 0 or
when
less
I'm taking
than 0.
an odd root,
so notice the difference
a can be anything but 0.
The first one, we were taking
so the cubed root of negative 8 is negative 2, because negative 2 times negative 2 times negative 2 is in fact negative 8.
When I'm taking
if a is
root,
negative and n is even, there are no real roots.
Is negative 2, because negative 2 times
negative 2. The square root of negative 4 is not a real number, meaning I cannot find two real numbers that are exactly the same and multiply them together and get negative 4. Because if I take two numbers that are exactly the same, two positive numbers multiplied together is a positive. Two negatives multiplied together is a positive.
I cannot find two real numbers that are exactly the same and multiply them together.
If a is 0, I don't care what n is, doesn't matter.
Two positive numbers multiplied together.
The nth root of 0 is 0. The fifth root of 0 is 0.
Is a positive.
Know your perfect squares, 1, 4, 9, 16, 25, 36, 49, and so on. Those are called perfect squares because they have integer square roots, right? Because the square root of 36 is 6. That's why 36 is a perfect square.
Know your perfect squares.
The numbers 1, 8, 27, 64, 125, those are perfect cubes because there is some number when multiplied together, some integer number multiplied together 3 times will get you 1, 8, 27, 64, 125, and so on.
The numbers 1, 8, 27, 64, 125.
Some properties of radicals. Again, these are hard to see. If you go into your syllabus and click on the document, you can actually see this document and get a better version of it and a lot easier to read. I don't want to spend a lot of time on this because
properties
it's
of
really
radicals,
difficult
again,
to read. We'll
hard
just
to
go through and look
see.
at examples.
If you go
And as
into your
examples pop up, I'll
syllabus
talk about them.
and click on the document, you can actually see this document, get a better version.
So here are some
a lot easier
radicals
to
we need to simplify.
read.
So letter A.
I don't want to spend a lot of time on this.
I'm taking the square root of a number times the square root of another number.
As examples pop up, I'll talk
because the index is the same, I can actually multiply the radicands or multiply the inside together. So the square root of 8 times the square root of 2 is the square root of 16.
The square root of a number times
and the square root of 16 is 4
because
the 4
index
4
is
16.
I can actually multiply the radicands or multiply
letter
the
B,
together. So
I'm taking the cubed root of 5, but I'm going to cube that answer.
And the square root of 16
essentially what happens here
4
is
cubing
a cube
16.
root is going to kind of cancel that radical. So the answer is simply going to be 5.
I'm taking the cubed root of 5, but I'm going to cube
part
that
C,
answer.
This is the cubed root of x cubed. Well, I don't have to, but I can rewrite this as the cubed root of x cubed. So you'll notice that part C and part B are very, very similar. Okay, so if you have a radical on the inside, if you have an exponent on the radicand, you can actually take that outside and do the cube root of the number first and then cube that answer. Regardless, the answer for part C is going to be
so if you have a radical on the inside, if you have an exponent on the
part D, it's a little different. When you're dealing with even powers and even indices,
the answer for part
remember
C
you cannot take the square root of a negative number.
Part D,
you cannot take the sixth root of a negative number. So in this case,
even powers and even indices,
it's very similar to part C. So you might think, well, the answer is just y. Well, here's the problem. If I say the answer is just y, I'm implying that y can be any number. But it can't, because I cannot take the sixth root of a negative number. So I have to make sure that this y is not negative. So to make sure that the y is not negative, the answer to this would be the absolute value of y. And again, you only have to worry about that if the index is even. So we have an even index
the
here.
y is not negative, the answer to this would be the absolute value of y.
That happens to be the same as the power, right? So when that happens, the result is absolute value bars.
Even. So we have an even index here.
When the index is odd, I don't care. Because remember, you can't take the odd
root as the power, right?
Of a negative
so when
number.
that happens, the result is absolute value bars.
And here are the answers. As you can see, on part A, I got 4. On part B, I got 5. Part C was X, and part D, absolute value bars, again, because that index was even.
And here are the answers.
An expression involving radicals is in the simplest forms when the following conditions are satisfied. Number 1, all possible factors have been removed. Number 2, all fractions have radical-free denominators. When we have a final answer, we cannot have a radical in the denominator. To take care of that, we're going to do something called rationalizing the denominator. And the index of a radical is reduced. So it's possible to start off with a problem that's like the fourth root of something, and then when we get done, the answer is going to be a square root.
To take care of that, we're going to do something called rationalizing.
To simplify a radical, factor the radicand into factors whose exponents are multiples of the index. Write the roots of these factors outside the radical. The leftover factors make up the new radicand.
To simplify a radical, factor the radicand.
Radical expressions can be combined by adding or subtracting. Just like when you were adding and subtracting x plus x is 2x, right? X and x, it's the same. So x plus x gives you 2x. A lot of times when you're working with radicals, think of them as variables. For example, if I just asked you, hey, what's x? Well, I don't know. I need some more information to give you a value to give you a value of x. Well, right now, tell me exactly, what is the value of the square root of 2? Well, I don't know. It's somewhere about 1.414, but I don't know exactly. And that's exactly right. So if you'll treat a radical like a variable. It'll kind of help you make sense of combining them. Okay. To determine whether two radicals can be defined, we have to simplify first.
And that's exactly right. So if you'll
So here's an example. I want to know what the cubed root of 24 is, and it's all worked out here.
To determine whether two radicals can be defined, we have to simplify
I can
first.
rewrite 24 as 8 times 3.
So here's an example.
8 is a perfect cube. 2 times 2 times 2 is 8.
What the cubed root of 24 is.
So 8 is a perfect cube. 3 is a leftover.
Well,
there are no perfect cubes that go into 3.
Rewrite 24 as 8 times 3.
I can rewrite 8 as 2 cubes.
A perfect cube.
Now folks, this is what the book says to do. This is how they teach this.
8 is a perfect cube. 3 is
if you know your perfect cubes, it's not a big deal. But what's happening here is if I can write 8 as 2 cubed,
I could rewrite
then I know the cubed root of 2 cubed is 2, which means that 2 is going to come out.
This is how they
Similarly, if you just know your perfect cubes and you know the cube root of 8 is 2, then you can just take it out right there and skip that step that I just kind of went around with the red line. Regardless, either way you do it, you still have that cube root of 3 left behind. And so there's your final answer.
And you know the cube root of 8 is 2.
Another way I've done this in the past is instead of writing it as one radical like they did in this first step, I could also say, well, the cube root of 24. That's equal to, I know that 8 goes into 24, and 8's a perfect cube, so I'm going to say the cube root of 8 times the cube root
I could also say, well, the cube root of 24.
Forgot the index. Sorry about that. So if you'll notice, I've done the same thing, but I've broken it up. So by breaking it up this way, I see that the cube root of 8 is already by itself, so that's just 2. And then I have the cube root of 3 left on the inside there.
Sorry about that.
And I tell my students this all the time, you know, there's more than one way to get the right answer on any problems in algebra. The best way is the one that you understand. So, you know, pick a method and stick with it and go. Part B. I'm doing the fourth root of 48, which means I'm looking for what's the biggest perfect fourth power that goes into 48? Well, 16. 16 is a perfect fourth power because 2 times 2, which is 4, times 2 is 8, times 2 is 16.
Which means I'm looking
so 2 to the fourth power is 16, and 16 times 3 is 48. I'm going to scroll down for the rest of this problem.
Well, 16. 16 is a perfect fourth power because 2 times 2, which is 4,
so down,
2 is 8, times 2 is 16.
Top, you've got the fourth root of 16 times 3, which is the same thing as the fourth root of 2 to the fourth. Obviously, the fourth root of 2 to the fourth is simply 2, and I'm left with a fourth root of 3 left behind.
Top, you've got the fourth root of 16 times 3, which is the same
Part
thing
C,
as the fourth root of 2 to the fourth. Obviously,
I have the square root of 25 x cubed. So we've got numbers involved and we've got letters involved. When you're dealing with letters, what you want to do is realize that for this problem, the index is 2. So if I have x cubed, 2 does go into 3 with 1 left over, right? So because 2 goes into 3, I can rewrite x cubed as x squared times x. Because x squared times x is x cubed.
2 does go into 3.
Now x squared is a perfect square.
Over, right? So
because 25 is also a perfect square.
I can rewrite
and again, if I was doing this problem, unlike the example, I would say, well, the square root of 25
because x squared times
5
is x cubed.
The square root of x squared
now,
is
x squared is a perfect square.
There are no perfect squares that go into 3 or x, so they stay inside the radical.
And again, if I was doing this problem, unlike the example,
the textbook,
I would say, well,
what they like to do is rewrite 25x squared as a single thing.
There are no perfect squares
squared.
That go into 3
Well,
or
x. 5x
so
times 5x, that is 25x squared, which means that 25,
that
5x
what they like to do is rewrite 25x squared.
Whatever you're comfortable with, I'm good with that.
5x
Part D,
squared,
the cubed root of 24, a to the fourth. Well, notice
squared,
that I've got a to the fourth power. 4 is bigger than 3, so 3 in fact does go into 4, not evenly. Because if you take 4 divided by 3, you got 1 left over. So what we're going to do here is break off an a cubed and leave an a behind because a cubed times a is a to the fourth. And 8 is a perfect cube. 2 times 2 times 2.
So what we're going to do here
8a cubed
is break off an a cube
are both perfect
and leave
cubes.
an a behind.
3a, neither one's a perfect cube, and it can't take anything out of it. So the 3a is going to be just sticking around.
Is a perfect cube. 2 times 2
again,
times 2.
they rewrote 8a
So 8a
cubed as
cubed
2a in parentheses cubed
cubes.
because 2 cubed is 8 and a cubed is a cube.
Out of it, so the 3a is
and by writing it this way, I can see that the 2a does come out because
again, they rewrote
a perfect cube is simply going to be 2a.
2a.
And the 3a will be left behind inside the radical as shown in this next step.
A cubed. And by writing it this way, I can see that the 2a does come out.
And part E, I'm taking the fourth root of 5x to the fourth power.
And the 3a
so because I'm taking the fourth root of something raised to the fourth power, we would think, well, the answer is simply, what are we taking the fourth root of? Or what are we raising to the fourth power?
And part
so in this case, we'd say, well, the answer is going to be 5x. But, again, this guy is even. And they're the same. So because of that, we need to have absolute value bars.
So in this case, we'd say, well, the answer is going to be 5x. But, again,
well, obviously, 5 is 5. So I don't need to leave the 5 inside the absolute value bar, so I can take it out. So the final answer is just 5 absolute value of x. When you're doing this, you need to make sure you're taking the absolute value of your variables.
Well, obviously, 5 is
take
5.
the absolute value
so
of your constants.
So
if that happened to be a negative 5 in there,
answer is just 5 absolute value of x. When you're doing this, you need to make sure you're taking the absolute value of your variables, and then of course take the absolute
combining
value
radicals.
Of your constants. So if that happened to be a negative 5 in there,
I cancel some of this out, and we'll actually work it out. Okay, I'll leave the words to the step there, but let's work through this. 2 times the square root of 48 minus 3 times the square root of 27. Okay, well, the way that's written, I can't do anything with it because the square root of 48 and the square root of 27 are different. So just like x and y are different. If I said, hey, what's x plus y, the answer would be
2 times the square root of 48 minus 3
if I said, what's 2x minus 3y, the answer would be, well, it's just 2x minus 3y. You can't combine anything. However, looking at the square root of 48 and the square root of 27, I see that there are perfect squares that go into those. Okay, and so what that would look like is 2 times the square root of, let's see, 48. Perfect square that goes into 48 would be 16. 16 times 3, right? 16 times 3 is 48. So I'm going to rewrite this as 16 times 3.
Let's see, 48. Perfect square that goes into 48
3 times the square root of
16.
Let's see, perfect squares that go into 27. 9 is a perfect square. 9 times 3 is 27.
Times 3 minus 3 times the square root of. Let's see.
So looking at this, I have 2 times the square root of 16 times 3. Now notice on this problem, I have a 2 in front of the radical. Well, the square root of 16 is 4.
So looking at this,
the square root of 16 is 4, but I already have a 2 there.
The square root of 16
so
times 3.
what's going to happen here?
Now notice on this problem,
4
I have
is going
to
be multiplied by the 2.
Well, the square root of 16
which gives me 8,
4.
And I still have a square root of 3 left behind.
The square root of 16 is
minus
4, but I already have a 2
the next one.
So
the square root of 9 is 3. But I've got to multiply that 3 by the 3 that's already there. So 3 times 3 is 9, or 3 times negative 3 is negative 9. However you want to look at that, that's fine.
The next one.
And that would be
the square root of 9 is 3. But I've got to multiply that 3 by the 3 that's already there.
Now we look at this and say, okay, well, 8 square roots of 3 minus 9 square roots of 3.
However you want to look at that, that's fine.
That would be negative 1
square root of
square roots of 3.
3 left behind.
And there's nothing to simplify there. Say, okay, I might have skipped a step that they did, but there's your answer. So 2 square roots of 48 minus 3 square roots of 27 is the same thing as negative square roots of 3. A little suggestion for you. If you want to be able to check your answers, if you will just simply type the original
2
problem
square roots of
into
48
your
minus
calculator
3 square roots
and
of
get a
27
value,
is the same
it's
thing
going to be
as
some ugly decimal. It doesn't matter. And then
a little
type in your
suggestion for
answer.
you. If you want to be able to check your answers,
Hopefully it's the
if you
same
were to
ugly decimal
simply
answer, right?
type
If you get the
your
exact
original
same
problem
decimal answer or the
into
exact
your
same
calculator
right
and get a
whatever answer it
value,
happens to
it's
be
going to be some
on
ugly
this, you
decimal.
know you've
Well,
got
it
the
doesn't
problem right.
matter. And then type in your
Part
answer.
B, we are doing
Hopefully it's the same
cube
ugly
roots.
decimal answer,
Now I'm
right?
just going to go ahead and
So
move this
if you get
box
the
and then
exact
talk about
same
this one.
decimal answer or the exact same
So are there any
whatever answer
perfect
happens to be
cubes that
on
go
this, you know
into
you've got the problem right.
16x? Well, I can't do
Part
anything with
B,
the x
we are
because
doing
3 does not go into 1. Because
cube
remember, that
roots.
is x
Not
to the
so
first
move
power
this
there.
boxes
So
and
I
talk
can't do
about this
anything
one.
with the x. However,
So are there
16.
any perfect cubes
16
that go
would be
into
8 times 2.
16x?
8's a perfect
Well, I can't do
cube
anything
because
with
2
the
times
x
2 times 2.
because 3 does not go into 1. That
54.
Is x to the first power.
Any perfect cubes
so
that go into 54?
However, 16.
3.
16 would be
times 3
8 times 2.
times 3
8's a perfect cube
is 27.
27
goes into 54. 2 times.
54.
X to the fourth.
That go into 54.
X to the fourth does have a perfect cube in it. I could rewrite x to the fourth as x cubed
is 27.
times x.
27 goes into
X
54.
cubed is a perfect cube.
Times. X to the fourth.
Here's what we've done.
X to the fourth does.
We've rewritten it as the cube root of 8 times 2x. 8 times 2 is 16, and there's the x. On the other one, the 54 is 27 times 2. 27 times 2 is 54.
We've rewritten it as
and x cubed times x is x to the fourth.
Times 2x. 8 times 2 is 16.
Find the cube roots. The cube root of 8 is 2.
The 54
the cube root of 27x cubed.
27 times 2 is 54.
The cube root of 27 is 3. And the cube root of x cubed is x.
Find the cube roots.
So because the cube root of 8 is 2, we brought a 2 out, left the 2x behind. Because the cube root of 27 is 3, and the cube root of x cubed is x, we brought the 3x out, left the 2x behind. I want to point out something here. When you're doing your problems, don't forget the index. I see students get kind of lazy and you start working a problem, all of a sudden you start forgetting to write that 3 as the index. Okay? So when you do that, you just turn the cube root into a square root. So keep an eye on that. Okay, so now we look at this. I have
I see students
2 times the cube root of 2x minus 3x times the cube root of 2x.
So when you do that,
now,
you just turn the cube root into a square root.
And the true definition of like terms, they're not like terms. One of them is the cube root of 2x, and the other one is x times the cube root of 2x. However, what they like to do here is they like to say, well, they both have cube roots of 2x. So what if I was to factor the cube root of 2x out?
However,
by factoring out the cube root of 2x, I'm left with 2 minus 3x. And that's what you're going to see on this next step.
What if I was to factor the cube root
out
of 2x out?
The cube root of 2x.
By factoring out the cube root of 2x, I'm left with
And when you're doing your homework, that's what they're going to want to see as well. So when you're doing your homework online there, make sure you factor out that perfect cube, perfect square, perfect fourth, or whatever it is.
2x, and there's your 2 minus 3x. And when you're doing your homework, that's what they're going to want to see.
Rationalizing the denominator. Okay, as stated earlier, when solving problems, you cannot have a radical in the denominator. So there's some things we have to do to get rid of it. If the denominator takes the form of either a minus b root m or a plus b root m, you're going to have to multiply the top and the bottom by the conjugate.
So there's some things we have to do.
So the conjugate of a minus
if the denominator takes the form
b
of
root
either
m is
a minus b root m or a plus b root m.
The conjugate of a plus b root m is a minus b root m. So basically what they're doing here with the conjugates is, if you think back to factoring and differences of squares, that's kind of what we're doing.
B root m is a plus b root m.
If a is 0, meaning I don't have a constant, all I have is that radical term.
So basically
if all I have is a radical term, then all you have to do to rationalize the denominator is multiply the numerator and the denominator by that radical. You don't have to worry if there's a constant in front of the radical. It doesn't matter. If it's a monomial and it's just some constant times a radical, all you have to do is multiply the numerator and the denominator by the radical, and that'll clean it up. If it's cube roots, to rationalize, you're going to have to find factors that generate a perfect cube.
And it's just some constant.
And we'll do some examples of those.
All you have to do is multiply the numerator and the denominator by the radical.
Okay, so let's
if it's cube roots,
zap this real quick.
To rationalize, you're going to have to find factors that generate
let's
a
work
perfect
part
cube.
A.
And we'll do some examples of this.
I want to rationalize the denominator.
Okay, so
I have 5 over 2 cubed roots of 3. Well, this is a simple one. I don't have a constant in the denominator. All I have is a radical. And it's just a square root. Well, to get rid of the square root of 3, I would simply multiply by the square root of 3. Because the square root of 3 times the square root of 3 would be 3.
I don't have a constant in the
anything
denominator.
to do to the bottom, you must do to the top. So I'm going to multiply the top
And it's just a square root.
The square root of 3.
Well, to get rid of the square root of 3, I
the
would
top
multiply
is now
by
5
the square root of 3. Because the square root of 3 times the square root of 3 would
divided by the bottom, which is 2.
But anything you do to the
times
bottom,
the square root of 3 times the square root of 3, which is 3.
Multiply the top by
so obviously that would be 5 square root of 3.
The top is now 5
over 6.
Square root of 3.
5 and 6 don't reduce.
Divided by the bottom, which is 2.
There's nothing I can do with that.
Times the square root of 3 times
Part
the square
B.
root of 3, which is 3.
Part B, I am dividing by a cube root.
Square root of 3.
And so what I want to point out here is,
reduce,
you can't do exactly the same thing we did on part A. If I just said, well, I'm just going to multiply the top and the bottom by the cube
part
root
B, I am
of 5.
dividing by
Let's think about what that happens. What happens when you do that?
And so
the cube root of 5 times the cube root of 5 would be the cube root of 25.
Do exactly the
25 is not a perfect cube, so that didn't help.
If I just said, well, I'm just
so multiplying by the cube root of 5 is not going to be beneficial.
Well, let's think about what that happens.
However, because my index is 3, if I can get a 3 as the exponent on my 5,
so multiplying by the cube root of 5 is not
so if I could have
beneficial.
5 to the 3rd power,
however,
that would be a perfect cube. So instead of multiplying by the cube root of 5, I'm going to multiply by the cube root of 5 squared
on my 5, right?
But
so
if I do that to the bottom, I have
5
to do
to
it
the 3rd power. That would be a perfect cube. So instead of
so what that gets
by
me, the top is going to be 2 times the cube root of 5 squared is 25.
Squared.
And the bottom is the cube root of 5 times the cube root of 5 squared. Well, my bases are the same. They're both 5.
So what that gets me,
when the bases are the same, you add the exponents. The exponents are 1 plus 2, which is 3. And so I'm going to go ahead and write it that way. My denominator is the cube root.
And the bottom is the cube root of 5 times the cube root of 5 squared.
And by doing that, you can see that the cube root of 5 cubed is going to be simply 5. So my final answer would be 2.
And so I'm going to go ahead and write it that way. My denominator
25
is the cube root of
over
5 cubed. And by doing that, you can see that the cube root of 5 cubed
and that's
is
it
going
for
to be
part B.
5.
Now, I covered up the textbook's work on part A, but you can see that in your document if you download it off the syllabus. Part B is going to be on this next slide.
And that's it for part B.
And you'll see they did exactly what I did. The exact same answer.
The textbooks work on part A, but you can see that in your document if you download it off the syllabus. Part B is going to be on this next slide. And you'll see they did exactly what I did when we got the text. So
we started off with the square root of 5 minus the square root of 7 over 2. I want to point out something here. On this example, what we're doing is they're telling us to rationalize the numerator. What's going to happen here after rationalizing the numerator is we will end up with a radical in the denominator, and that's okay. Because for this particular problem, they're telling us to rationalize the numerator. Think about it, folks. Rationalizing a numerator, rationalizing the denominator, it's the same thing. They're just reciprocals of each other. So what I'm about to do this problem, I could do to the same problem if it was 5 over the square root of 5 minus the square root of 7. So don't get hung up on the fact of the process. The process is exactly the same. So for this problem, the numerator is the square root of 5 minus the square root of 7. the conjugate to the square root of 5 minus the square root of 7 is the square root of 5 plus the square root of 7. So what's going to happen here is we're going to multiply the top and the bottom by the square root of 5 plus the square root of 7. And again, we're doing the top and the bottom because essentially we're multiplying by a 1. So on the top, I'm going to go ahead and work out what's happening here and why we choose to multiply by the conjugate. If you think about it, the numerator is a binomial. The square root of 5 minus the square root of 7 is a binomial. If we multiply it by the square root of 5 plus the square root of 7, it's another binomial. So if you remember, when multiplying binomials, we use the phrase FOIL.
If you think about it,
so if I was to FOIL this, the square root of 5 times the square root of 5 would be the square root of 25. There's first times first.
So if you remember,
outside times outside would be
the phrase FOIL.
Minus
so if I was to
the square root of 7 times the square root of 5 times the square root of 5 times the square root of 7, so that's the square root of 35.
There's first times first.
Plus
outside times outside would be
hold on a second. Let me back
minus
up. Outside times outside is the square root of 5 times the square root of 7. That would be a positive square root
35
of 35.
Plus
inside times inside, that's the negative 7 and negative 5. So that would be the
outside
negative square root of 35.
The square root of 5 times the square root of 7. That would be a positive
times last would be
of 35.
Minus the square root of 7 times the square root of 7 is the square root of 49.
Inside. That's the negative 7 and negative 5.
If you'll notice what happens there, by multiplying by the conjugate,
plus
the outside and the inside actually cancel each other out because we have a plus square root of 35 and a minus square root of 35. They're not perfect squares, but they cancel anyway, so it doesn't matter. So what's left? Square root of 25 is 5.
The outside and the
minus the square root of 49 is 7. So we're going to end up with a 5 minus 7 in the numerator, which means no radical.
They're not perfect squares.
On the bottom,
anyway, so it doesn't matter. So what's left?
We have
square root of 25 is 5 minus the square root of 49 is 7.
2.
So we're going to end up with a 5 minus 7 in the numerator, which means
plus
no radical. Okay.
Square root of 7.
On the bottom.
So again, back to the top, the square root of 25. Well, that was 5. Outside and inside cancels, minus 7 over 2 times the square root of 5 plus the square root of 7.
So again, back to the top, the square root of 25.
Well,
that was
5 minus 7 is negative 2.
Outsides and inside cancels, minus
over
7.
2
over
times
2
square root of 5 minus
the square root of 5 plus the square root of 7.
And if you'll notice here,
well,
I have
5
a 2
7
divided by 2. They cancel.
Over.
That's just a 1. So my final answer,
the square root of 7. And if you'll notice here,
negative 1.
I have a 2 divided by 2.
Over.
They cancel.
The square root of 5.
That's just a 1.
The square root of 7.
So my final answer.
And I did, in fact, rationalize the denominator, which is what they wanted me to do.
Negative 1 over the square root of 5 minus the square root of 7. And I did, in fact, rationalize
exponents. So far, all the exponents we've been dealing with happen to be integers. Some are positive. We can deal with negatives. It doesn't matter. Now we're going to look at rational exponents, which means my exponents are going to be fractional. Definition of a rational exponent says if a is a real number and n is a positive integer such that the principal nth root of a exists, then a to the 1 over n is the same thing as the nth root of a. So what's going on here? When you have a rational exponent, the bottom number is going to be your index. A to the 1 over n. N is the bottom number. Therefore, n is my index.
So what's going on here?
If m is a positive integer that has no common factors with n, then a to the m n, m over n power is the same thing as a to the 1 over n raised to the m power, which is the same thing as the nth root of a. Again, the bottom number is the index.
A to the m
now I'm talking about the top number, m. That is the power. You can write that power on the whole
Which is the
radical
same
when you
thing
put it in
as
parentheses,
the nth
or
root of a.
you
Again,
can
the
write that
bottom
m
number is the
on the
index.
a inside the
I'm
radical.
talking about the
And
top
that's one of
number.
the
The top
properties
number
we did a
m,
while ago anyway.
that is the power.
If you're taking the nth
You
root
can write
of a
that
to the
power
m,
on
that m can come out.
the whole radical when you
So
put it in parentheses,
if I'm doing the
or
nth root of a
you
to
can
the
write
m,
that
I can
m
take that
on
m,
the a inside the radical. And that's one of
put
the
it on the
properties we did
outside
a
like
while ago
this,
anyway.
okay?
If you're taking the nth root of a
So
to
it's just
the
a
m,
combination of some
that m
properties.
can come
But
out.
the important thing here is to remember, the
So
top number is the
if
power,
I'm doing the nth
the
root
bottom
of a
number
to
is
the
the
m,
index.
I can take that m and put it on the outside like
And
this,
here it is.
okay?
b to the
So
m
it's just a combination of some
over
properties.
n.
But the important thing here is to
Power
remember, the
is
top
the
number
m,
is the power,
the index is
the
the
bottom
n.
number is the index. And here it is. B
For instance,
to the m over
2
n.
to the 1/2 times
The
2 to the
power
1/3.
is the
It's a little
m,
hard to read.
the
Let me
index
rewrite that.
is the n.
2 to the 1/2 times 2 to the 1/3.
For instance,
folks, our properties are exactly
2
the
to the
same.
1/2
When the
times 2 to
bases
the
are the
1/3.
same,
It's a little hard to
you
read.
keep
Let me
the
rewrite that.
base and add the exponents. So 2 to the 1/2
2
times 2
to
to
the
the 1/3
1/2
would be 2
times
to the
2
1/2
to the 1/3.
plus 1.
Folks, our properties are exactly the
To
same.
add
When
1/2
the
and
bases
1/3,
are
I need
the
a common
same,
denominator.
you
That
keep
common
the
denominator would
base
be 6.
and add the exponents.
1/2
so 2
is
to the
3/6.
times 2 to the 1/3 would be 2.
1/3 is
to the
2/6.
1/2 plus
3/6 plus
1/3.
2/6 is.
To add 1/2 and 1/3, I
5/6.
need a common denominator.
Okay.
That common denominator
So
would be
make
6.
sure you combine, reduce,
1/2
whatever
is
needs to be done.
3/6.
And if I wanted to write that as a radical,
2/6.
I could write
3/6
that
plus
as
2/6 is
the 6th root
5/6. Okay.
of 2 to the
So
5th power.
make sure you combine, reduce, whatever needs to be done.
2 to the 5th
and if I
power is
wanted to write that
32,
as a
so I could actually
radical,
write this as the 6th root
I
of
could
32.
write that as the 6th root
We'll be looking at more of those in a little bit.
of 2 to the 5th power. Okay.
All right.
2 to the 5th power is 32, so I can actually write this as the 6th root of 32. We'll be looking at more of those in a little bit. All right.
Okay, so part A, I have a negative 32 raised to the negative 4/5 power. The bottom number is the index. The bottom number is 5. So because 5 is odd and that 32 is negative, I can still work. If that had been negative 3/4 power, I'd have a problem with that negative 32. But because my index is going to be 5, we're good to go.
5 is odd, and the 32 is negative, I can still work. If that had been
negative 32 to the negative
power,
4/5
I'd have
power.
a problem with that
We could
negative
write
32.
that as.
But because my index is going to be 5, we're good
Again,
to go.
5 is the index, negative 4 is the power. So the negative 4 is the power. I could actually write that as,
power.
to get rid of the negative exponent, I could write it as a fraction. We're not doing that yet. So the 5th root of negative 32 is negative 2. Because negative 2 times negative 2 times negative 2 times negative 2 times negative 2 is negative
to get rid of the negative exponent,
negative 32. And negative 2 to the negative
so
4th power, that would be the same thing as writing it as 1 over negative 2 to the 4th power. So again, notice what happened there is that negative 2 was what's being raised.
Negative 32. And negative 30.
Sorry about that. I raised my hand up while I was going. The camera could follow me. Okay. We have a negative 2 raised to a negative power. To get rid of the negative power, we take the negative 2, bring it down to the denominator. I now have negative 2 to the 4th power. Negative 2 times negative 2 is 4.
Okay.
Times negative 2 is negative 8.
To a negative power.
Times negative 2 is 16. So negative 32 to the negative 4th power is
negative 2 times negative 2 is 4.
This next one, we have a negative 5x to the 5/3 power times 3x to the negative 3/4 power.
Negative 32
the first thing you want to do here is
power
multiply. So multiply our like stuff together. Negative 5 times 3 would be negative 15.
We have a negative
and then x to the 5/3
power
times x to the negative 3/4. We're going to add those exponents together.
Here is multiply.
Because when the bases are the same, you add the exponents.
Negative 5 times
So we're
3
adding
will be
5
negative
thirds
15.
and a negative 3
And then
fourths.
x
That
to the
becomes
5
5 thirds minus 3
times x
fourths.
to the negative 3/4.
Doing
We're
the
going
math
to
on
add
that
those exponents
gives
together.
you
Because when the bases are the same, you add
x
the
to the
exponents.
11/12th power.
So we're adding
And then, of
5
course, it tells
thirds
us
and a
that
negative
x can't be
3/4. That
0.
becomes 5 thirds
Right?
minus 3/4.
And the
So doing the
reason
math
x
on
can't
that
be 0
gives you
is because
x to the 11/12th power.
of this one right here.
And then, of course, it tells us
Because
that
if you think about
x
it,
can't be 0.
3 times x to the negative 3/4 power, what that means
And
is
the reason x can't be 0
3 over
is
x to the positive 3/4 power, right?
of this one
And
right
so
here.
if x were 0,
Because if you think about it,
for the second
3
piece of the
times
problem
x to the
here, I would
negative
be
3/4
dividing by
power,
0,
what that means
which is undefined. And so
3
sneaky stuff like that will happen to you in
x to the
algebra where you have
positive
to start
3/4
thinking
power,
about, okay,
right?
are there any
And
problems?
so if
Are there any
x were
stipulations I have to put
0,
on the variable?
for the second piece of the problem here, I would be dividing by 0, which is undefined. And so
Part C, I'll just leave it like it is.
happen to you in algebra,
If I
where you
have,
to start thinking about,
we're
okay,
going from rational,
are
we're
there any problems?
going from
Are there any
rational,
stipulations I could put on the
we're
variable?
simplifying rational exponents here. So the 9th root of a to the 3rd. The bottom,
Part
the
C,
index is the bottom number. The power is the top number.
We're going from
So the
rational,
9th root of a
going from
cubed is the
rational,
same thing as a to the 3/9.
simplifying rational.
But 3/9
exponents here.
reduces. 3/9
So the
reduces
ninth
to
root
1 over
of
3.
a to the 3rd.
The top number is
The
the power,
bottom-
the bottom number is
index
the
is the bottom
index.
number.
So the 3
The
goes on
power
the
is the
on
top
the index
number.
there.
So
So
the
the 9th root
of
of a cubed is the same thing as the cube root of a.
But 3/9
And that's what I was
reduces.
talking about
3/9
earlier when we talked
reduces to 1
about
over
making
3.
sure that your index was
The
reduced.
top number is the power,
So
and
this
the
one
bottom number is
reduced.
the index. So the 3 goes on the
Part
index
D,
there. So
we're
the
taking
ninth root of
the
a cubed is
cubed
the same
root
thing
of
as
the
cubed
square
root
root.
of
So
a.
let's think about that.
And that's what I was talking
If
about
you're
earlier.
taking
We
the
talked about,
cube root
making sure
of
that your
a
index was
square root,
reduced.
of
So this
mathematically
reduced.
means multiply, right?
Part D,
So the cubed
we're
root
taking
of the square
cubed
root. If you
of
think about
the
what those
square
fractions
root.
look
So let's
like,
think about
you
that.
have the
If you're
cubed root,
taking the cube root
3 is your
of the
index, so
square
that'll be your
root.
denominator,
Of mathematically
of
means multiply, right?
the square root.
So the cubed root of the square root.
So if you took
think about what
1/3
those fractions
times
look like,
1/2,
you
that
have
would give you
the cubed root,
1/6. And
3
that
is your
is
index, so
where
your denominator,
the 6 came from.
of
Okay? So the
the
cubed
square
root of the square root of 125 is the same thing as the
So if you
6th
took
root of
1/3
125.
times 1/2, that would
But
give
125
you
can be
1/6.
rewritten as a perfect
And
cube.
that is where
125
the
is the
6
same
came
thing as
okay?
5 cubed.
So the cubed
Well,
root
because
of
I
the
can
square root
write
of 125 is
125
the
is
same thing
5
as the 6th
cubed,
root of 125.
I now have an index of 6,
But 125 can be
a power
rewritten
of
as
3,
a perfect cube.
which gives me 5 to the 3 over 6
125
power.
is the same thing as
3 over 6
5
reduces
cubed.
to 1/2.
Well, because I can write
1/2 would simply be
125
the
is
square root of
5
5.
cubed,
So the cubed
I
root
now
of
have
the
an
square
index
root
of
of
6,
125 is
a power of
the
3,
square root of 5.
which gives me 5 to the 3 over 6 power. 3 over 6 reduces to 1/2. 1/2 would simply be the square root of 5.
Simplifying rational
So the cube
exponents.
root of the square root of
On part
125
E,
is
I have
the
two
square root.
bases that are the same. I have 2x minus 1 and 2x minus 1. Those bases are raised to different powers. One of them is a 4/3 power, and the other one is a negative 1/3 power.
On part E, I have two bases that are the same.
Because the bases are the same,
and 2x minus 1.
I'm going to add the exponents.
Those bases are raised to different powers.
4/3 plus a negative
power,
1/3, which is the same thing as 4/3 minus 1/3, is 1. Well, 2x minus 1 to the first power is just 2x minus 1.
Add the exponents.
However,
4/3
x can't be 1/2.
plus a negative 1/3,
Where'd that come from?
which is the same thing as 4/3 minus 1/3,
Okay.
is 1.
Because
Well, 2x minus 1 to the first power is just 2x
it's
minus
negative
1.
exponent. Remember, negative exponent means pass it through the fraction bar. So 2x minus 1 to the negative 1/3 power is the same thing as 1 over
let's look at this
2x minus 1
this negative exponent.
to the
Remember,
1/3
negative
power.
exponents means pass it through the fraction bar.
You cannot
so 2x minus
divide
1 to the
by 0.
1/3 power is the same
0
thing as
to the 1/3 power would be 0. What would make 2x minus 1 0?
To the 1/3 power.
2x minus 1
You
cannot be 0.
Divide by 0.
Add 1 to both sides.
1/3 power would be 0.
2x can't be
What would make
1.
2x minus
Divide
1
both sides by 2.
0?
X cannot
2x minus 1
1/2.
cannot be 0.
And they mention it right here below,
Add
but
1
they
to
don't
both
kind of go into the
sides.
detail that I just did. But that's what's
2x
going on.
Can't be 1.
Remember, you cannot
Divide both
divide by
sides
0.
by 2.
What would make it 0?
X cannot be
1/2 would make it 0.
And they mention it right here below, but they don't
Folks,
kind of
that
go
is
into
the
detail
end of
that I
this
just
section.
did. That's what's going on.
The next thing I have are some practice
Remember,
problems.
you cannot divide by
So,
0.
as
What
I've
would make
stated
it
in the
0?
past, it'd be a good idea to go ahead and stop the video at this point.
1/2.
Work the practice problems on your own. After you're done working the practice problems, come back
Folks,
to the video,
that is the end of this
and I'll be
section.
working them for you.
The next thing I have are some practice
Okay,
problems.
so I'll work these for you now. Simplify the radical expression, the square root of 125. Are there any perfect squares that go into 125? The answer is yes. 25 is a perfect square. 25 goes into 125.
Simplify the radical
5
expression, the
times.
square root of 125. Are there any perfect squares that go into 125? The answer is yes.
The square root of 125 is the same thing as the square root of 25 times the square root of 5.
Square.
Square root of 25 is
25
5.
goes into
The square root of 5 is, I don't know.
5
Square root of
times.
5. And we're done with that one.
So,
number 2, we're doing a cube root. Are there any perfect cubes that go into 40? And the answer is yes.
The square root of 5 is,
because 8 is a perfect cube. 2 times 2 times 2.
Number 2.
Go ahead and write that as 2.
We're doing a cube root. Are there any perfect cubes that go into 40?
So 2 cubed is 8.
Yes.
And 8 times
because
5 is 40.
Cube.
And the cubed root of 2 cubed is 2.
We'll go ahead and write that
and
as
the cubed root of 5 is
kind of mix it up
root of 5.
Okay.
Again,
So
folks, I write it a little bit different from the textbook.
And
I actually
8 times
separate the perfect squares or
5
perfect
is
cubes
40.
and write them under different radicals,
And
where
the
the
cubed root
text
of
tends to
2
write them all
cubed
together.
is 2, and the cubed root of 5
Number
is
3.
the cubed root of 5. Again,
Simplify this radical. Any perfect cubes that go into 192. Perfect cubes that go into 192.
Text tends to write them all together.
Well,
number 3. Simplify this radical. Any perfect cubes that go into 192. Perfect cubes that go into 192.
64 times 3 is 192. 64 is a perfect cube. So I'm going to rewrite this as 4 cubed root of 64 is a perfect cube. 64 times 3, so I'm going to put a cube root of 3 over here. So I've taken that 192,
so I'm going to rewrite this
I've broken it into the perfect cube piece and the stuff that's going to be left behind. X cubed. Well, x cubed is a perfect cube, so I'm going to put it in the perfect cube side.
64 times 3, so I'm going to put a cube root of 3
plus the other side.
So I've taken that 192,
cube root of
I've broken it into
any
the perfect
cubes in 81.
Yes.
Yes.
X
27
well,
is
X
a perfect
cube.
cube.
Is a perfect cube.
27 times 3 is 81. So 27 is a perfect cube.
Plus the other side. Cube
7
root of
times 3 is
any
81.
perfect cubes in 81.
X cubed is a perfect cube, so I'll put the x cubed right there.
27 is a perfect cube. 27 times 3 is 81. So 27 is
and let's see what comes out. The cubed root of 64 is 4.
Times 3 is
4
81.
cubed is 64.
So
I'm taking a 4 out, but I've already got a 4 there. So because I'm taking a 4 out, and there's already a 4 there, that's going to give me 16.
And let's see what comes out. The cubed root of 64
of x
is
cubed
4.
is x. And
4
here's my
cubed
root
is 64. So I'm taking a 4 out, but I've already got a 4 there.
Plus,
so because I'm taking a 4 out,
the cube root of 27 is 3.
16.
The cube root of x cubed is
the cubed
x.
root of x cubed is
and
x.
there's the cube root of 3.
And here's my cube root of 3.
And if you'll notice here, I have,
the cube
in
root
fact,
of 27
two
is
exact-like
3.
terms. Both of these, I have 16 of these x cubed roots of 3's, and then I have 3 more of these x cubed root of 3's, which gives me a total of,
notice here, I have
19
in
of
fact
x
2 exact-like
cube root of
terms.
3's.
Both of these, I have 16 of these.
A little bit different from a
cubed
problem we
roots of
worked
3's,
earlier
and I have
in this
3
lesson.
more of these
This one
x
actually
cubed
does
root of 3's.
simplify into one term. We don't have to worry about
total of
factoring something out and having an odd-looking answer.
of these x cubed root of 3's.
Rationalize the denominator. I've got a cubed root of 5 in the denominator. To get rid of a cubed root of 5, I need to turn that 5 into a 5 cubed. Well, to turn that 5 into a 5 cubed, I'm going to multiply the bottom and the top by the cubed root
Rationalize the denominator.
5
I got a
squared.
cubed root of 5 in the denominator. To get rid of a cubed root of 5, I need to turn that 5 into a 5 cubed.
So the top, I have 125.
Well, to turn that 5 into a 5 cubed, I'm going to multiply the bottom and the
times
top
the cubed root of 5 squared. Well, 5 squared is 25. I can't do anything with that.
5 squared.
Divided by the bottom, I have the cubed root of 5 times the cubed root of 5 squared, which is the cubed root of 5 cubed, which is going to give me a 5. So I now have 125
divided by the bottom.
25
I have the cubed root of 5 times the cubed root of 5 squared, which is the cubed root.
Pay attention always. You know, if you ever can reduce, you must. 125 divided by 5 is 25. So my final answer is
cubed root of 25 over 5. But notice,
25.
Pay attention always. You know, if you ever can reduce, you must.
Number 5, rationalize the denominator. I do have a binomial in the denominator, so I'm going to have to multiply by the conjugate. So the conjugate of this is going to be the square root of 15 plus 3.
Number 5, rationalize the denominator. I do have a binomial in the denominator, so I'm going to have to multiply by the conjugate.
3 times
so the conjugate of this is going to be the square root of 15 plus 3
over the bottom. Remember, we do the conjugates, and when you FOIL these, the outsides and insides cancel. So all that's going to be left are the outsides, first and last.
Plus 3.
So the square root of 15 times the square root of 15
over
is
the
15.
Bottom. Remember, we do the conjugates.
Negative 3
and
times
the
positive 3
the outsides and insides cancel. So all that's going to be left
so I
are
now
the outsides.
Have 3.
First and last.
15.
So the square root of 15 times the square root of 15 is 15. And then minus
15 minus
3
9.
times the positive 3 is negative 9.
15 minus 9 is 6.
So I now have 3.
3 over 6 reduces to 1/2.
Plus 3
so
on
I have the square root of 15.
Over 15 minus 9.
Plus 3.
15 minus 9 is 6.
And you might notice that when I worked this
6
problem, I never
reduces to
distributed
1/2.
that 3 at the beginning.
So I have
when I had that 3 times the square root of 15 plus
square root
3.
of 15
I mean, sure, I could have distributed that and got to 3 root 15
all
plus
over 2.
9. But many times when you're doing
And you
problems
might notice that when I worked this problem, I never distributed that 3.
So it's best to not multiply out until later.
3. I mean, sure, I could have
Because when things
distributed
are
that and got
factored,
to
that's
3
when
root
you
15
can
plus 9.
Cancel.
But many times when you're doing problems like this, canceling is a possibility.
Write the
So
radical
it's best to
expression
not
as a
multiply
rational exponent
out
expression.
until later. Okay? Because the things that are factored, that's when you can, in fact, cancel.
So I want to get rid of the radical. So I have an x to the 4th here.
Write the radical expression.
I'm going to rewrite the cubed root of x squared.
Expression.
The 3, the index, is the denominator. 2 is the power. So this is going to be multiplied by
I'm going to get rid of the radical.
x to the
so I have an x to the 4th
2/3.
here.
2 is the power. It goes on top. 3 is the index. It goes on bottom. Excuse me. My bases are now the same.
The denominator.
So I can add those
so this is multiplied by
exponents together.
X to
I have
the
x to the 4
2/3.
plus
2 is the power. It goes on top. 3 is
thirds.
the index. It goes on bottom.
4 would be the same thing as
my bases are now the same, so I can add those
12/3, right? So that gives
together.
me
I have
12/3 plus
4
2/3.
plus 2/3.
Which gives me x to
4
the
would be the same thing as
14/3.
12/3, right?
And so I started with a radical expression.
12/3 plus
I've ended up with a rational exponent expression. 14 over 3
X
does
to
not
the
reduce, so I'm done with that one.
14/3.
Number 5, simplify the rational exponent
So
expression.
I started with a radical expression.
So I have a negative exponent. I'm going to change that first.
Expression.
So I have 1 over
does not reduce
25 to the 3/2 power.
Number 5, simplify the rational
Well, that's the same thing
expression.
as 1
so
over
I have a negative exponent. I'm going to change that first. So I have 1
the square
over
root
25
of 25
to the 3/2 power
cubed.
Well, that's the same thing as
well, the square root of 25 is
over,
5. So 1 over 5
the square root
and 5 cubed is
of 25.
125. So the final answer for number 5 is 1
well, the square root of 25 is 5.
125.
So 1 over 5 cubed.
All right, folks, that's it for this particular lesson.
125.
Guess I'll say bye. The camera's not following me. Make it follow me again. All right.
1 over.
Yeah. So that's the end of this lesson.
125.
Hope everything's working out for you great. If you have any questions, please reach out. That's what I'm here for. Call me, text me, email me, whatever. I want every one of you to be successful in this class. Y'all have a great day now.
That's the end of this lesson. Hope everything's working out for you great. If you have any questions, please reach out.